thank you for joining me today. My main goal for today is talking about one of the latest launches we got. So this family, Praesto AP+ family resins. But as you can see, there's a lot of other products that we have already in the portfolio. So all of them are Affinity resin that you could be using for protein, for monoclonal antibodies and related molecule purification. So if you have any question about that portfolio, please don't hesitate to jump around to our booth, and we will be happy to talk to you about them. So for 100 years, Ecolab has been around providing solutions for a customer, solutions that are basically based on science sounding solutions, and then also thinking on data-driven solution that we're putting to our customers. So today we're going to be discussing one of those solutions that we put for the biopharmaceutical industry, basically focusing how can they improve their processes, how can they improve their cost efficiencies. So the Praesto AP+ family resin is supporting upon four major pillars. So one of them is the reduce of cost, basically thinking on improved process economics. And also it is a family of resin that are easy to implement and also fits easily in the legacy products and high-tech processes. Another of the pillar is the technical equivalency. So the ligands that we're having in our products in this family, those ligands are easily introduced in the already existing process. So they support seamless transition with a performance which is equivalent to the already established processes. So the other pillar is basically the high capacity. So these resins are having I would say a binding capacity that is on top of the available binding capacity that you can find in the market, and it's also based on the quite robust ligands. So you would expect a very interesting large life expectancy for those resin. So within this family, we have two main products. So one of the products is having 80 micron beads, and these micron beads are exceptional for a very good flow properties. So we're thinking of that. So we're thinking in a process that can run really, really fast. So we're talking about, we will see more technical data down below in the presentation, but where this resin excels is in applications where the column bed height is above 20 centimeters. So we're talking about something about 25 centimeters bed height, where you can run that resin in that regard. So the other component in the family is 50 micron beads. With this 50 micron bead, you will get a couple of good, I would say, benefits. One of them is a very high binding capacity. And the other advantages of these small beads is related to the resolution. So you will have a proteinate resin that will still have a very high binding capacity, as also showing a very good resolution for separating the molecules. The other thing is this resin will excel in applications where the bed height will be ranging between 10 15 centimeters. This is where you can get the most profitability in terms of efficiency and in terms of productivity. So when the scientists go to the lab, they're aiming to answer a few questions, no matter if you're thinking on a second generation of process or you're developing a fully new process from the scratch. One of questions like how much protein can I put in this resin? This is binding capacity, or how much of that protein can I recover later on in the dilution? So we're talking about yield, or for how long can I use that resin? So that's lifetime. So other question would be, for example, how pure is the product that we can recover from that resin? That's purity. So we're going to be trying to answer some of those questions across the presentation. This is the answer to the first one. So we were talking about how much protein we can load in that resin. So as you can see here, we have binding capacity when we're comparing three different resins. We have AP+50, which is on the top. We have AP+80, which is in the middle. We have one of our toughest competitors, which is in the bottom here. A couple of things to keep in mind. So we're having a resin, for example, if we are talking about AP+50, it is a resin that has a very interesting binding capacity. We are talking about roughly 70 grams per liter at 6 minutes residence time. You can extend that to 80 grams per liter if you extend the residence time to 80 minutes. But what is interesting here is having a very high binding capacity at short residence time. So we're talking about 50 grams per liter and only 3 minutes residence time. That would give you opportunities for implementing that approach for process intensification. The other thing is, for example, equivalency. The ligand that we have in both resin, in the 50 micron version and the 50 micron version, it is a resin that performs quite similar to the standard that you would expect from the market in terms of binding capacity, in terms of life expectancy, in terms of elution profile, thinking on, for example, elution color volume, thinking on HCC removal, DNA removal. So it is a ligand that is easy to accommodate within an existing process. So talking about compatibility, so we are also testing this resin against all the competitors that we have. As you can see here on the chart on the left, we have included 2 more competitors. And as you can see, there's a line in green. This competitor, there's a reason why you're seeing a higher binding capacity here. And it's because that resin, it has smaller beads. When you're having smaller beads, then you will have a larger surface area, a lot more amount of ligand for increasing the binding. So that's why you're having a larger binding capacity. The downside of this is that you may have a lot of fines in this kind of resin because this is not an agarose bead, so there's a lot of fines there. It's a resin that might be a little bit tricky to handle when you're thinking on scale up and manufacturing. And then we tested this with monoclonal. When you see the monoclonal performance on the right, you will see that the resin is for the 80 micron is compatible in terms of performance with the competition. But as you can see, for the AP+50, you have a very, very good binding capacity. That applies for both monoclonal antibodies and polyclonal antibodies. Keep talking about how compatible or how similar this ligand can behave compared to previous processes. Here you're seeing, for example, the elution profile. Thinking on chart on the left, this big chart here, we're talking about yield. So as you can see, the yield is practically compatible across the range. As I said before, this is a very consistent ligands that we have in our products here. And then you see when you look at the log reduction of HCCPs, is practically having the same performance. So again, if we're thinking on the second generation processes where you're looking for a solution that helps you with the with handling or reducing the cost of the process, this is something that you can have here. That's also applicable to the protein A leakage. As you can see here, the protein leakage is quite compatible to what we have already in the market. Another thing that is also talking about how compatible the performance is regarding the elution pole volume. So we're having, most of the time, we're having about 2 column volumes as a standard in elution in our processes. And this is something to compare to, something to keep in mind. Now jumping to another of the question at the very beginning. So we're talking about alkaline stability for this line of products. We got AP+50 here. We tried it with 0.1 molar sodium hydroxide. We tried as well with 0.5 molar sodium hydroxide. The way that we performed this experiment was by soaking the resin in the cleaning agent for about 20 hours. Then we took a sample, we run a DBC, and then we put it back again for another 20 hours before taking the sample again. We did that for about 100 hours. So as you can see, the stability of the ligand for 0.1, it means that we kept the resin for about 100 hours. And then the dynamic binding capacity practically didn't reduce more than 10%. So we have in here about 90% of the initial binding capacity by even after being disposing the resin and the ligand for about 100 hours in the CIP solution. As you can see, for the 0.5 molar, obviously this is in more harsh conditions, and for proteins sometimes can suffer in those CIP conditions. As you can see, we still remain in about 60 hours with 0.5 molar. So we normally recommend having about 15 minutes contact time for every CIP cycle. So if you think about, let's say, 60 hours, that's accountable for more than 100 cycles. We did the same kind of experiment with the AP+80. Remember that we're using the same ligand here. What we're only changing is the bit size. Here, again, we are with 0.5 molar. We can still retain about the 90% of the binding capacity, even when you are soaking the resin for about 100 hours in the cleaning solution. When we're jumping to 0.5, the result is a little bit different. We can get about to 60 hours, still maintaining about the 80% of the initial binding capacity, but it's quite comparable to the our main competitors that we have in this range. The other question that we were having at the very beginning was related to how long or how fast we can run the process. So here we are having, let's focus first in the 80 micron. As we said before, this is a resin that it has very good flow properties. We normally, where you can get the best from this resin is when you're running the process in columns that having a higher bed height. So something between 20, 25 centimeters. At that bed height, we're running the flow velocities that is ranging between 300, 400 centimeters per hour. This is quite respectable flow rate for running the process in at least for a capture step. And then the other resin, the AP+50, obviously you have a smaller beads. When you have a smaller beads, you have a higher back pressure. So this is where we normally recommend running this resin at a bed height between 10, 15. You can run it at 20. That's fine. There's no problem. The only thing is you need to be aware that then the flow rate that you will be achieving with this resin will be around 200 centimeters per hour. If you drop in the bed height, you will be able to run between 300, 350, even to 400 centimeters per hour. So that fits easily into a process intensification consideration. So you can get a very good profitability in terms of increase. The word escaped me. Yeah, you got increased productivity if you're running those conditions. So now we are talking about process intensification. We know that the industry has been put on pressure because they need to deliver product to the market as fast as possible and as in the amount that is needed for the industry. So the industry is embracing the process intensification. There's many ways that you can intensify your process. You can use, for example, a multi-column in parallel format where you're loading the column, and then when that column is been fully loaded, you pass it to the rest of the step, and then you take the other column and start loading that other column. So in the way, normally when you're loading, the loading time is normally the step that takes longer in a chromatography process, mostly for the capture step. So in that way, you will be saving time because you don't need to wait for the column to be loaded again to start the remaining steps in the process. The other thing is multi-column chromatography. You know this for a while now. It's been a concept that has been around, basically, where you're just trying to maximize the binding capacity that you have in the column. When you're running a normal process, you only utilize about 20, 30% of the capacity of the resin. By doing multi-column chromatography, you guarantee that you're utilizing more than 80, 90% of the binding capacity. And then the other way that you can intensify the process is running something that we call rapid cycling. And you can do that by dropping the bed height of a column, so you can cycling the resin a lot faster. You have many more cycles, and you will be utilizing the lifetime of the resin longer. This is more applicable when we're thinking, for example, in when a process is in clinical studies. When you run a clinical study, you normally don't run many cycles. You run only the cycles you needed to produce the amount of product that you need for running the clinical trials. So in this scenario, this is where you can get the most profitability in terms of rapid cycling. So let's get back for a while to that first chart we introduced you. I want you to pay attention to a couple of things here. So we're having a binding capacity of 50 grams per liter at only 3 minutes. This is pretty much equivalent to the 6 minutes resident time for 60 grams per liter at 6 minutes resident time for the competition. Also at 70, you can get at 6 minutes resting time, you can get up to 70 grams per liter. If you push it a little bit higher to 10 minutes resting time, you can get up to 80 grams per liter. So let's put this resin into different scenarios. So we're talking about the scenario where you're dropping the bed height, another scenario where you're reducing the bed height, but also you're playing around with the column diameter, and then playing around also with the dual velocity loading. So all of this is to try to increase the productivity of the resin. We're going to be using the competition as a benchmark. So all the data that we're having there are going to be compared to the benchmark from the competition. So the first scenario, we're just bringing, the only thing we're doing here is reducing the bed height, okay? So let's focus in the lower row. The lower row is our benchmark. Here we're having a column thinking on a clinical runs. So this is a process that has been running 2,000 liters by reactor with the titer about 5 grams per liter. Okay, so for that you would need, let's say, roughly about 56 liters, for example. We're gonna be packing the competition resin in a 60 centimeters column diameter by 20 centimeters bed height. And we're gonna be running that process at 6 minutes resin time, where you see the competition of 50 grams per liter, okay? So now think about our resin running 10 centimeters lower, okay? By dropping the bed height 10 centimeters, that means that we're using only half of the resin, okay? Because you're using only half of the resin, we're gonna be running that at 3 minutes resin time. We know that 3 minutes resin time can be equivalent to 50 grams per liter, so we are matched here, okay? Because we are dropping the bed height and we are increasing the resin time, we need to run now 14 cycles to get the same processing. So we still need to run or need to process these 2,000 liters. As you can see here, we're having exactly the same processing time, no changes there, but focus on the total resin cost. Okay, we're dropping the cost here about 80% only by reducing. So obviously we need to start from the least price of the resin. So that gives you a hint about how much you can manage your cost, your process cost here. But then, as I said, we're dropping the column volume by half, so we're having a very good cost savings of about 80%. On top of that, because we are doing rapid cycling, we're increasing the productivity in terms of grams per liter per hour. So that productivity has been increasing about 90%. And still, you can feed this process easily in your same system. We're talking about the same column, we're talking about the same buffer consumption, we're talking about the same system. So it's easily incorporated in the system, in the process that you have already. Let's tweak this a little bit further. So now we are having exactly the same column, 60 centimeters column diameter, 10 centimeters bed height, but we are increasing the process rate or the flow rate. We're reducing the residence time now. So increasing the residence time. When you have 6 minutes, then we have 70 grams per liter. When you're increasing the capacity here, that means that you no longer need to do the 14 cycles that we were doing before. Now we're running only 10 cycles. When you're running less cycles, you're saving buffer. So we're talking about a reduction in buffer consumption about 30%, okay? Then we're keeping the same reduction in the cost because we're still having the same column volume, but then we're still having about 25% reduction, increase in the productivity, sorry. And still, we can feed the same process. Okay, let's do another more tweaking. Let's change the column dimensions completely. Now we're using 45 centimeters column diameter, but increasing a little bit the bed height to 15 centimeters. That means that we are even further reducing the column volume and still having able to process the 2,000 liters that we have for the very beginning. In this scenario, we are increasing the residence time so we can achieve about 80 grams per liter in this process. By doing this, we are still, even when we're increasing the residence time, there's no major impact here in the total processing time, okay? And because we are even maintaining practically the same amount of cycles, we are still having a very good reduction or decrease in the buffer consumption. We're talking about 40% in buffer consumption. Think about sustainability, for example. We're reducing the buffer consumption. We're reducing the consumption of water. We're reducing the amount of chemicals that we're putting in the process. We're also reducing the amount of cycles. So from the sustainability point of view, there's also another benefit that you can find here. So, and then let's challenge ourselves, okay? As I said before, there's many ways that you can increase productivity. One of the productivity is doing what we call dual loading. So when you load about 80% of the feed available at, let's say, 6 minutes residence time, and then the other 20% of the remaining feed, you will load it really, really fast. So that means that you will be reducing the total process time, but then you will be increasing the overall binding capacity. In this scenario, you can increase productivity close to 80% and still reduce the buffer consumption for about 20%. So within those scenarios, you can see there's a lot of increases in productivity you can achieve by only dropping the bed height, okay? And you can do that with this resin here because we have a very good mass transfer. We can have about 50 grams per liter with only 3 minutes residence time. So then wrapping up, this is the first slide we got at the very beginning. So we have a product family here that is basically thought to drive the product cost down. You can do that by improving process economics, and it is, as I said, it's a resin that is easily fitting within the normal or the standard process that is being used for a while. So you also have here technical equivalency, where the resin is performing quite similar in terms of binding capacity, in terms of elution profile, reduction of the contaminants, and it's also a resin that is having a very good lifetime comparable to what you have in the market today. So for me, that's basically all my talk today. If you have any question, please don't hesitate to ask.